Okay, here the recording in progress. Share the screen. All right, so we are over here. Quick word about the quiz. So I graded all the quizzes. You should have gotten an email reply back from me on the quiz and also the solutions. So if you did not, then please let me know right away. Okay, so you know the way the quizzes work. This week we're not having a quiz because we're having a test. So exam 3 is this Friday. We're already in week 8, believe it or not. So we'll be roughly halfway through the semester right here. Okay, so I was going to finish up 3.5. There's just one more problem I was going to do. And then we just have 3.6 left. So we have plenty of time to finish everything. That being the case, there's a good chance it will end early today and maybe other days this week. If I get way ahead, maybe I'll just start sneaking in some of chapter 4, which is on trig. That's our longest chapter, as you know, as you can see here. Okay, so I'm going to mark off 3.5. I'll finish that today. And you've seen enough of my exams now as to how they work. And I just noticed that this thing is frozen now. So I have to try to unfreeze it after the previous hour also. So we'll take a little time out. So bear with me as I try to fix this. I have to do this and maybe come back in and try to share the screen again and see if it works. And okay, looks like we're back in business. All right, well, you've already seen a couple of my exams, so you know the way they work. So you're responsible for this material. You have to submit at least 70% of the homework. Again, that's really a joke because I do almost 70% of the homework anyway. Okay, and the questions are very similar to the homework. I usually give about 10 questions. Let's see, there's 5 sections, so maybe 2 questions per section, roughly. That's not a promise, but that seems like a reasonable thing for me to do for the exam. Okay, and you all have to show up to the Zoom session. So as I said, lectures, all of these days are optional, but not for the exams. The exams, you actually have to show up. I need to see your face. And the usual, have your first and last name in the, just as in my row sheet, keep yourself muted, have the true background behind you, and keep yourself muted. If you have any questions, put them in the chat. Okay. And I shouldn't have to say too much about it since you've seen a couple of exams. You know the way it works by now. Okay. All right, so let me do one more problem in 3.5 and then start some of 3.6. So the last problem I wanted to show you was 1 over radical x minus 2. I think it was problem 21. X at a negative 1/2, which means 1 over radical x. And then minus 2 after that. Okay, so x at a negative 1/2 minus 2. You see, I messed up. I put a plus at first. It's supposed to be a minus. These are minuses. All right. X at a negative 1/2. The negative means put it in the denominator, and 1/2 means square root. So it's 1 over radical x minus 2. All right. So first I'm going to look at 1 over radical x, because once I have that, I know what to do with that. Just move it 2 units down, right? So 1 over radical x. Now, how can I possibly graph 1 over radical x? Well, I'm going to pick numbers that have nice square roots. So I plug in 1. 1 over square root of 1 is 1. 1. Plug in 4. Square root of 4 is 2. 1/2. Plug in 9. 1 over 3. And this gets a little tricky, but 0.01. The reason why I picked 0.01, the square root of 0.01 is 0.1. Okay, 0.1 times 0.1 is 0.01. Excuse me. So the square root of 0.01 is 0.1. 1 divided by 0.1 is 10. Okay, so it shoots up like crazy. So in red, is a very rough sketch of 1 over radical x. Okay, so it looks like it approaches the x-axis as an asymptote. It also approaches the y-axis as an asymptote. Here's the point 1, 1. And then I just go 1 over radical x minus 2, shove the whole graph 2 units down. So 1, 1 becomes 1, negative 1. So I have that in green. So everything else is the same general shape. So in green, here is 1 over radical x minus 2. This does have a horizontal and vertical asymptote. So a horizontal asymptote. Well, let's see, it used to be the x-axis, which is the same thing as saying y equals 0. So I move down 2 units. The horizontal asymptote becomes y equals -2. The vertical asymptote, well, it shoots up toward the y-axis. If I move down 2 units, it's still going to shoot up toward the y-axis. So x equals 0 is the vertical asymptote. Okay, and then let's see. The original directions, sketch the graph, give the intercepts and asymptotes. Okay, so we're done with the asymptotes. We got 1 and 1 horizontal asymptote, vertical asymptote. And now the intercepts, axis intercepts are just intercepts. So we plug in for that. Okay, there is no y-intercept. Y-intercept means x equals 0, but take a look, x equals 0 is impossible, right? So the graph never touches the y-axis. Gets really close, but doesn't quite touch it. It does look like there's going to be some x-intercept. Looks like it's here. So where's here? That means y equals 0. So set 0 equal to this expression. 0 equals 1 over radical x minus 2. Add 2 to both sides. 2 equals 1 over radical x. Square both sides. 2 squared is 4. 1 over radical x squared is 1 over x. Okay. I can play this trick of just switching these two around. If you've never seen that before, that's an acceptable algebra trick. You can just switch these two around. So x is equal to 1/4. Right, so 1/4 comma 0 is the x-intercept. So yeah, you're allowed to switch these around, or you could also say if two things are equal, their reciprocals are equal. So you can flip both sides. If you flip this, you get x. And if you flip this, you get 1/4. So x is equal to 1/4. Okay, I'll dig just a little bit deeper on this. If you ever have A equals B over C, then you're allowed to just switch these two. C equals B over A. Okay. If you have A equals B over C, C equals B over A. If you want to convince yourself of that, multiply both sides of this one by C, and you get AC equals B. If you multiply both sides here by A, you get the same thing, AC equals B. So yeah, here we are. I'll give you a real number example, which I think will bring it home even more. 5 is equal to 15 over 3, right? What happens if you switch these two around? 3 equals 15 over 5. So, oh yeah, of course it's true. Right, so that's all I'm doing here. Okay, so if you ever get a situation like this, there is an algebra trick that you can just switch these two around. Put the A down here, put the C over here. Like here, 5 equals 15 over 3. You're allowed to swap the 5 and the 3, and then it looks like that. 3 equals 15 over 5. Right, so that's another way of looking at solving this problem here. I'm allowed to just swap these two and say x is equal to 1/4. X is 1/4. Okay, problem's finished, but I was going to dig a little bit deeper about quickly drawing the reciprocal. And so if we temporarily ignore the green, just look at the red square root function, radical x. We know radical x looks something like that. And then I can play my rules of reciprocal, right? Here's 1, 1. That's 4, 2 for what it's worth, but we don't really care. All right, so here's radical x. How do I graph the reciprocal? 1 over radical x. Okay, so whenever y is 1, I get the same point. Whenever x is 0, the other graph will be undefined. And then the increase-decrease game, right? This one increases, this one must decrease. If I go backwards, this decreases, so this must increase. So there's a quick graph of 1 over radical x. As it were. Okay. All right, folks, I'm actually done with 21, which now means I'm completely finished with section 3.5. So we only have one section left before the test on Friday, 3.6. It's on complex numbers. I'll introduce some of that today, and we have the rest of this week to work on it. And if necessary, I'll even sneak in some of trig. But if you want to ask questions for review, you certainly may do that as we get further down the week. Okay, so introduction 3.6, complex roots of polynomials. So first, some review of intermediate algebra. I is defined to be the square root of -1, which also means that I squared is -1. If you want to put these on your cheat sheet, you may for the test. And if you haven't already done so, start building your formula sheet, your cheat sheet for the test on Friday. Okay? So you're legally allowed to cheat for me, the limitation being 1 sheet of paper, standard size, 8.5 by 11, both sides, put anything you want. Okay? All right, so I is the square root of -1. You say that can't happen. That's true. It can't happen for real numbers, but it can happen for imaginary numbers. And now we have something called a complex number. Complex number, z equals a plus bi. What's that? This is the real part. This, as you can guess, is the imaginary part because there's an I to it. Okay. So it'd be something like 3 plus 5i. I can't call it real because there's an imaginary part. I can't call it imaginary because there's a real part. There's a real part and an imaginary part. So we make up this new word, complex number. And of course, the English word complex already has, its own meanings, like complicated or whatever. But here, complex is used in a sense that there's a real part and imaginary part. So those are called complex numbers. We write it as a funny-looking C, like this. You know how we write the funny-looking R, right, for all real numbers? So a funny-looking C with 2 lines for complex numbers. Okay? There's a real part and there's an imaginary part. Okay. All right, page 179 has a quadratic formula again. You can put it or not. You've already seen it before. And I don't even know why they put it like that. It's a lot more easy to do plus or minus, right? But be that as it may, I would just put the plus or minus stuff. Okay, complex conjugate, I'll talk about it as we need it. So you don't really have to put that down, in my opinion. Complex arithmetic, I think it's pretty straightforward if you just know the properties of I. So I don't think you need to put that down either. Okay. Let me start showing you the homework, which is 1 to 55 odd. So just 2 pages. Page 184. So there we go. I think that's sort of readable. And then 185. And there we go. Okay, so first my introduction. So my take on things. So complex numbers. So as the text said, I is the square root of -1. It's an imaginary number, non-real. It has the property that I squared is equal to -1. So in standard form, when you write an answer with complex numbers, I should never be to an exponent. You should never leave an answer as I squared, I cubed out of the fourth, because it's going to be broken down in terms of I, or you just lose the I altogether. And so standard form for a complex number is A plus BI, where A and B are real. This is called the real part. This is called the imaginary part. Here's an example that I mentioned before. 3 minus 5i. This is the real part. This is the imaginary part. A and B are real numbers. But once you multiply it by I, it becomes imaginary. All right, as the text talked about something called complex conjugate. The complex conjugate of A plus BI is A minus BI, and vice versa. Okay, so these are called complex conjugates of each other. So what's so good about that? We'll see. Okay, we're going to end up multiplying together. You end up with something like A plus BI and A minus BI. Okay, and we know from algebra how to multiply x plus y, x minus y. It's x squared minus y squared. Okay, in fact, number 11 is a good example of that. I'm not sure we'll get to that today. But if you want a quickie idea of multiplying by a complex conjugate, here are conjugates: 2 minus 3i, 2 plus 3i. So 2 times 2 is 4. And then 3i times 3i is negative 9i squared. And I squared becomes -1. So you have -9 times -1, which is 4 plus 9, or 13. It's a real number.
So writing that in like standard form is just 13. It's not like 13 plus 0i or anything.
Correct. You can just write 13. 13 plus
Okay.
0i is acceptable, but it's simpler to just write 13, of course.
Cool. Thank you.
Okay, you're welcome. All right, now powers of I. Okay, this can get a little tricky, and again, you're welcome to put that on your cheat sheet if you wish. Okay, how do you raise I to a power? So again, your final answer should never have I to a power, because you're going to always pick it down. All right, so I to the 0, well, we already know from before, we want to keep true that anything raised to the 0 is defined as 1. And then we like to define I to the first power. We like anything to the first power just to be the same thing. So I to the 1 is also just I. Then the new stuff, we already declared back up here that I squared is -1. So again, I is the number that is the square root of -1. It's not a real number. It's an imaginary number. In other words, I squared is -1. So I squared, anytime I see I squared in the rest of these problems, it's going to be -1. And now that I have that, I can work out I to the third, I to the fourth, I to the fifth, and so on. Okay. So I cubed is I squared times I. Well, I already know I squared is -1. So I'm going to have -1 times I, or -I. So again, your final answer for I should not have a 2 or 3 or 4 exponent. It should just be I, or it's gone completely. I to the fourth. I to the fourth, well, I can write it as I squared times I squared. I now know that I squared is -1 here and also here. So it's -1 times -1, or 1. And I'm drawing an arrow as if indicated it now cycles back. Powers of I cycle every 4. Because now you don't get anything new. You just repeat yourself. So like I to the 5th, well, I can think of it as I to the 4th times I. And now that I know that I to the 4th is 1, it's the same as 1i, or I. So powers of I would just keep repeating in cycles of 4. You just keep going 1, I, -1, -I, cycle back 1, I, -1, -I, and so on forever. Okay. Which means we can even come up with a chart like this. Notice if I add 4 to the exponent, it ends up being the same thing. So I to the 0, I to the 4th, I to the 8th, I to the 12th, those are all 1. I to the 1st, 5, 9, 13, they're all I. I squared, 6, 10, 14. See what's happening? Once you start off with these basic 4, I to the 0, oops, I to the 0 is 1, I to the first is I squared is -1, I to the third is -I, and then you just cycle back 4, 5, 6, 7, 8, 9, 10, 11, and so on. Okay, so every exponent added 4 to it will give you the same value. So I squared, I to the 6th, 10th, 14th, those are all equal to -1. I to the 3rd, 7, 11, 15, and so on gives me -I. And again, if you want, you're welcome to put this on your formula sheet for the test if you want. Right, so I'll do some of the arithmetic problems involving I, and then that's about it for today. And so some of this stuff. First, I noticed this bar thing. What is this bar stuff? The bar means the complex conjugate. So that bar means complex conjugate.
So that literally means like to change the plus to the minus, right? Like I was really confused because I thought that was just to denote that that was a conjugate, not to make it into a conjugate.
Correct. So this is the same thing as writing 2 minus I. That's all.
Okay.
So this bar 2 plus I, keep the real part the same, but change the sign of the imaginary. So just pretend the problem says 3 minus 8I times 2 minus I. That's all. So it's just one more hoop to jump through, I suppose. Okay. Well, for problem 1, even if you never saw this imaginary stuff, -3 plus I plus 2 minus 3I, I just said, from what you know from algebra, go ahead and try it. If I said, go ahead and try it, you'll probably get it right. You will look at it and say, well, you know, I see some numbers and I see some I's. So why don't I add the numbers to the numbers and the I's to the I's? And if that's what you thought, you'd be right. Your -3 plus an I. I mean, it's like a letter, right? It's just like if there's an X. So I'll combine the X with the X. So same thing. I'll combine the I with the I and the number with the number. So -3 plus 2 is -1. And then 1I minus 3I is -2I. And just leave it. That's simple. And yeah, standard form, you give your answer with the real part first and the imaginary part second, because we don't like imaginary. We want to kind of put it off until the end. So it's always real, then imaginary. So if your answer ever has the I first and then the number, just turn it around. So it's real and then imaginary. That happens sometimes. In fact, that happens in the next problem. All right. Yeah, number 5. 3I times 2 plus I. All right, just distribute. And even if I never said anything about algebra, right, and said, you know, put down what you think it should be, well, you would go, oh, that times that, 6I. 3I times I, 3I squared. And you're right, so far, the only new thing is you can't leave your answer with an I squared. Anytime I see I squared, I change it to -1. So this is 6I plus 3 times -1. Okay. And the last little tricky thing is you're always supposed to write it in standard form as A plus BI, meaning real part comes first, imaginary part comes second. So -3 comes first, and then 6I comes after that. Okay. So that's the way you got to do that. So technically, this is not correct if I leave it like this. It's got to be real and then imaginary. All right, number 9 looks like FOIL. It is. These are both in standard form, real plus imaginary, real plus imaginary. I'll just FOIL like I did in Algebra 1, right? First, outer, inner, last. But there is going to be an I squared. So the extra complication will be that there's an I squared. And when there's an I squared, you change it to -1. That's all. You just have to watch out for that. So here we go. First, 6 times -3, -18. Outer, -12i, right? Inner, -15i. And last, that times that, 5i times a -2i, -10i squared. And there it is. I squared has to be changed to -1. So again, you don't leave your answer with any i's. So that's -1. So now I combine the real part and the imaginary part. So this gets changed to -10 times -1, which is +10. And yeah, -12i minus 15i is a -27i. So combine the real parts. Final answer, -8 minus 27i. And you can just leave your answer like that. Okay. All right, so yeah, let me dig a little bit more into the complex conjugates, and then I'll just about be done. So 11 says 2 minus 3i, 2 plus 3i. Let's see, where is it? Yeah, number 11 here. 2 minus 3i, 2 plus 3i. Okay, that's like a minus b, a plus b. So I don't have to do first, outer, inner, last. I just do first and last. 2 times 2 is 4. -3i times 3i. So -9i squared. And there's the I squared. I changed I squared to -1. So it's -9 times -1. 4 plus 9, 13. Real. Get a real number. Okay, so here's an important principle. Okay. So what's so good about this complex conjugate stuff? If you multiply a complex number by its conjugate, you always get a real number. You can prove it here. A plus bi times a minus bi, right? You get a squared minus b squared I squared. And then you see, aha, I squared. Anytime I see I squared, change it to -1. So it's a squared minus b squared times -1, negative, negative. So it's a squared plus b squared, which is real. All right, so the principle is this. If we multiply a complex number with its conjugate, multiply a complex number with its conjugate, you end up with a real number in your final answer. Okay. And there we go. All right, and folks, that was all I was going to do today. We got plenty of time. We only have one section left. Still got Tuesday, Wednesday, Thursday to knock off the rest. So plenty of time to do that. So I did up to roughly 11. So next time I'll do some more of these and then go from there. Okay, but otherwise I'm finished for today, folks, unless anybody has any questions. So does anybody have any questions for me right now? I can address them. Otherwise, we're going to call it a day. And again, you should have all gotten the quiz result from me. If you did not, let me know right away. I emailed you also the your score, and I gave a solutions video. I think it was on Saturday. So if you want to see the solutions to the quiz, the video has that. I usually do that also. Okay, any questions, please? Let me stop the share so I can see the chat. Okay. All right, any other questions? Otherwise, we're done, folks. All right, everybody have a good day, and we'll see you next time. Okay. All right, bye, everybody.
Thank
See you later.
Thank you, Professor.
Thank you. Bye.